is f of x. That is called function notation. We have used function notation. Well, you have used it for a long, long time because it's like it's on the second page of the Algebra 1 textbook. I mean, you've been exposed to this for a long time. This is read f of x. That's how we say it. But in your in our work that we've done before, we've had s of t, right? Now, and here was like a formula that we had. I'll just make up some numbers. Okay. By the way, what would the presence of this 10 right here tell me? The initial velocity was 10 feet per second. And what would this tell me?
Starting height.
The starting height was 3 feet above the ground, right? Now, the reason I'm putting this up here is because this is function notation. This says s of t. This is like f of x. And this indicates the height at time t. That's how functions operate. You give them an input value. So if I said s of 2, what would I be looking for? S of 2, what would that be? The height at time 2, at 2 seconds. The height at 2 seconds. That's how functions operate. There's an input, and then there's an output. All right, what else do you think of when you hear the word function? F of x, the notation, very good. What else do you think of?
G of x.
What?
G of x.
Okay, certainly we can use whatever letters we want. So f of x is the most common, probably because f and function, you know.
Yeah.
But we could have g of x, s of t,
Okay.
p of q. We could have any letters that we wanted. Bailey? A table of values, because this notation actually represents a set of ordered pairs. You have your inputs and you have your outputs. So in terms of this, the inputs would be the time and the outputs would be the height, right? In terms of this one, the inputs would be the x's and the outputs would be the y's, because f of x is just a different notation for y, right? Now, in these sets of ordered pairs, and that's what a function is, I mean, it's nothing more than a set of ordered pairs. It's a pairing. X produces y. Input, output, every time. There's a name for the set of inputs, and there's a name for the set of outputs. John? Domain and range. Okay? So in this problem, in the projectile motion problem, what's the domain? The domain is the time. What's the range? The height. Now, depending on the situation, you can make observations about your domain and range. Go back to this problem right here. What can you tell me about the domain? We've agreed it's the time. So tell me about the set of numbers that could be the time. Is it everything, all real numbers? Is your domain all real numbers?
You can have negative.
You can have negative time. Where would time start? 0. So what's your domain for this set, this situation? Your domain would be all of the t values that are greater than or equal to 0, right? Now what about your height? Same thing? Wouldn't you have to be greater than or equal to 0? Absolutely. Now, in a minute, we're going to talk more about domain and range. It's a hugely important topic, especially domain. In the beginning, we start with the assumption that our domain and range are all real numbers. And then we narrow it down from there based on the situation. So keep that in mind. We're going to talk about that a little later. Is every set of ordered pairs, though, a function?
No.
Why?
They can't have like repeating x values.
Exactly. So that's the definition of a function. Dan, this is like the biggest thing in mathematics. Do not act so bored. A function is a relation or a set of ordered pairs with no repeated first coordinates. Now, Dan used the word, Dan said there's no repeated x's. And that is perfectly okay. But this year, we are going to study ordered pairs that aren't x comma y. We're going to study a whole new coordinate system where our ordered pairs are r comma theta. There aren't even any x's in it. So that's why I like to say first coordinates. If you said x's, everybody knows what you mean. Nobody's going to count that wrong. But it's really the first coordinate, whatever that happens to be, that can't repeat. Okay? Now, graphically, that means, because we're going to do a lot of graph analysis in this chapter, a ton of it. When we analyze graphs, would that graph be a function?
Yeah.
Think about all the ordered pairs on that graph. Do any of them have the same x coordinate? No, and you can tell that because it passes the vertical line test. Remember the vertical line test? So if you have an actual set of ordered pairs, like if you had actual numbers here, you could tell if it were a function or not just by looking at these guys. If you have a graph, you can tell this by if it passes the vertical line test, right? What if you have an equation? I pulled this one out of the homework. Is this a function? That's what the question says.
No.
Is this a function?
No,
Why not?
you can't have x squared.
Actually, x squared is a parabola. Is that a function? Is a parabola a
Yeah.
function? Yeah, you absolutely can have x squared. You cannot have y squared, but you can have x squared. Trevor,
It's because of the plus minus,
what does that do?
because that means that you'll have an x value for the plus 3 and an x value for the minus 3.
It'll have a y value. Bingo. Trevor says if you put 1, the number 1 in here, and you go with the top equation, or the top sign, you get 4, right? But what if you put 1 in and go with the bottom sign? You get -2. Now both those points are perfectly okay, but what's true of them? They have the same x coordinate. So you're exactly right. You're exactly right. Good. Okay. More function vocabulary. Is there anything else you want to add to our conversation of functions? When we analyze functions, we look at lots of things. One of the things that we talk about is its domain. If I have a function like 3x plus 2, I told you a second ago that you are going to operate under the assumption that your domain starts as all real numbers, unless you do something or there's something in the equation that would change that. Now, what could change it? Well, we talked about one example. In word problems, you have to be careful because sometimes it just doesn't make sense for the variables to be negative, let's say, right? So we have to rule those out. So word problems are kind of their own animal. You have to just read the question and determine. But in terms of just straight up equations, you're walking down the hall and you find an equation. There are 2 huge domain red flags. If you have a radical, whatever is under it must be positive. Because you know what happens if it's not positive, right? We go into imaginary numbers and we don't want to go there. We can, we don't want to. We want to keep it real. So to keep it real, if you have a radical in your problem, whatever is under it has to be positive. Do I have a radical? Okay, so I don't need to worry about that. The other big red flag, and kids, these are huge red flags. If you have a fraction, whatever is in the bottom cannot be 0. Does this problem have a fraction? No. So it doesn't have a radical and it doesn't have a fraction. Its domain is the set of real numbers, and that's the symbol, in case you've never seen it before, for the set of real numbers. What about this one? again, you're walking down the hall and you find this. And somebody says to you, oh, you found a function. What's the domain? All numbers except 8. So you can write that many different ways. I am perfectly okay with you simply saying x can't be 8. Because if you tell me x can't be 8, I'm going to assume you mean x can be everything else. Now, if you want to look like a real mathematician, you'll say your domain is everything from negative infinity to 8, or from 8 to positive infinity. This says the same thing. So if you look at, your honors counterparts, they're writing it this way. And you are welcome to write it that way. This is the official way. But I'm perfectly good with this, because it means everything except 8. What if you're walking down the hall and you find, oh, by the way, that's going to show up in the graph. If you graph that, it's going to show up as a vertical asymptote. That's going to show up as a vertical asymptote. So when we graph this, and we're going to do it, we're going to put a vertical asymptote at x equals 8. What that does is split your graph into 2 pieces, the left side and the right side. So there'll be something over here, and there'll be something over here. If I graphed this, would it be split? Nope, it's going to go on forever and ever in both directions, all real numbers. As soon as you put a 0 in the denominator, you're going to pop in a vertical asymptote. That's going to cut your graph in half. Okay? What about this? I got a radical in there. What do we know about radicals? That's a huge domain red flag waving. What do we know about what's under the radical? It has to be bigger than or equal to 0. I should have said greater than or equal to 0, but it's got to be greater than or equal to 0. So this guy right here has to be greater than or equal to 0. You can take the square root of 0, as long as it's not in the bottom. Which tells me what about x? If x plus 1 has to be greater than or equal to 0, x has to be greater than or equal to, there's your domain. So if you're going to graph this picture, you have to pick x's that are bigger than or equal to -1. So what impact does that have? It's not an asymptote. It just says the picture starts here. This part of the picture is empty. There's nothing over here, it's blank. The picture starts right there. Now you're saying, Miss Ford, how'd you know that's what that looks like? This is one of your BFFs. You're going to know what it looks like too in a matter of a week or so. What if we had this? Now we got double trouble, kids. Tell me about this domain. Miss James.
So usually, x has to be greater than or equal to -2, but then x cannot equal 3.
And x cannot equal 3. You are exactly right. You are exactly right. The numerator tells me, oh, I got a radical. So x plus 2 has got to be bigger than or equal to 0, which means x is going to be bigger than or equal to -2. But I have a denominator that can't be 0, so I want to be bigger than or equal to -2, except I can't be 3. That would be your domain. Okay? Now, another word, so one of the words we talk about a lot is domain. Another word that we talk about a lot is bounded, which we've kind of already discussed, and continuity. And maximum, minimum, and increasing, decreasing. This is all function vocabulary. So I'm going to make up a picture. I'm just going to graph a function and make it up. And I am going to label some points here. This is -4, 0, and this is -1, 7, and 3, -2. Okay, I'm totally just making those points up, but I've got some kind of a picture that looks like that. Now let's talk about bounded. Just gut feeling. Look at that curve. Do you think that curve is bounded? Why not? The arrow goes down forever, ever, ever, and this one goes up forever, ever, ever. Take a look at my picture that I drew over here. What about this one in terms of boundedness? Well, it's certainly bounded below. It has a floor. It doesn't go past this point, right? Bounded below. What's happening here, though? It's going up forever and ever and ever, so it is not bounded above. To be bounded, you have to be both below and above. So this one would just be bounded below. Now, if we had, here's another one of your BFFs, get ready. This is called the logistic function. You're going to love it. But if you had this function, now there's a bounded function because it has a floor and a ceiling. Okay, do your best with the homework. Just give them a shot. There'll be a bunch of blanks, I know, but just read through them all and see what you can come up with. Have a good day. Do not forget Math League sign-ups.